All right, in this video series, we're going to learn about graphical models, which are a way of representing your Bayesian modeling setup. So if you remember in the last video, we talked about kind of the basics of Bayes' rule, how do you set up a model, and a little bit about how you do inference, right? Like we talked about maximum likelihood estimation, we talked about MAP, maximum a posteriori, minimum mean squared, all these different ways of reasoning about the hidden thing that you want given the data. In this video series, we'll talk about how do you actually set up more complex models, something more complex than just like, a bunch of yes, no's and some probability of being 1 or 0. And we'll use this idea of graphical models as a way to visually represent our models and capture important stuff that's going on in them. We won't talk about like, how do I actually figure out what's going on with the hidden parameters? We did that for the easy case last time, and we'll do that for more interesting and harder cases next time. Before we start, let's briefly review ideas of independence and conditional independence. So remember that two random variables being independent means that knowing one doesn't give you information about knowing the other. More specifically, knowing the value of one doesn't tell you anything about the probability distribution, the density function, the mass function of the other. So mathematically, we'll write this out as if we have two random variables, x and y, we say that x is independent of y, right? This symbol here means is independent. And this means that knowing something about the distribution of x doesn't tell me about the distribution of y. So for example, I can write p of x, y. The joint distribution of x and y is just the probability individual distributions multiplied together. Right? And this is sort of analogous to with events. You can think of, if two events are independent, then the probability of both is just the probability of one times the probability of the other. It's the same thing with random variables. So this is independence. You can imagine, let's say x is like the number of books on my bookshelf, and y is, I don't know, the average amount of rain this month, right? Like they're not really related. Knowing one doesn't really tell me about the other. If I know I have more books, it doesn't tell me like there's going to be more or less rain. Okay, that's independence. We also have this idea of conditional independence, right? So this is independence. And we also have conditional independence, which tends to be a lot more interesting. Conditional independence is the idea that, well, x and y, maybe they're independent, maybe they're not. But if I know z, then they are independent, right? If I know a third fact, then these two things are independent. And the way we write this out notationally is that x is independent of y, conditioned on z, right? So the same notation for conditioning that you've seen, we use for everything else. And here we're saying x is independent of y given z, right? And for example, you may have that, like if x is the attendance in an in-person class, and y is like how I get to campus, right? Back when, I used to go to campus. So you can imagine, knowing something about how I get to campus, does that tell you about the attendance in class? Well, on the surface of it, those two things don't sound related, but then we think about weather, right? If it's raining, then I'm probably not going to bike to campus. I'm probably going to like take the bus or something else. And if it's raining, attendance is probably also going to be lower. At least it has been in my experience. So maybe if x is how I get to campus, or I think I did that the other way around. Y is how I get to campus, and x is attendance in an in-person class, and z is the weather, right? So x and y aren't independent, but if I know that it's raining, then knowing attendance doesn't tell me anything about how I got to campus, right? If I know it's raining, then that already tells me that the distribution for attendance is going to be shifted lower, right? There's fewer people likely to show up. And if I know that it's raining, that already tells me that the distribution of how I get to campus is going to be skewed pretty heavily towards like options where I'm covered, right? Like taking a bus or something else, as opposed to like walking or biking. So knowing z already tells me something about how x and y change. And so once I know z, then they're no longer related. So this idea of conditional independence is really important. We often see it in cases where, z might be like the parameters of your model, and x and y might be two different observations, right? If I know, like, the simplest example is if I'm flipping a coin, if I know how biased that coin is, then knowing one flip doesn't tell me anything about the other, right? Like if I know a coin is really biased towards heads, the first flip is going to be probably heads. The second flip is also going to be probably heads. Knowing that the first one came up heads doesn't tell me anything about the other. But if I don't know how biased the coin is, then knowing the first flip tells me a lot, right? Like if let's say that, I have reason to suspect that maybe the coin's more biased, but I don't actually know. I see like the first few flips are all heads, then I think the next flip is more likely to be heads than tails, right? Knowing the first few changes my distribution on the other, right? I don't think it's just going to be fair anymore. Okay, so that's independence, that's conditional independence, and we'll talk about how these play out in graphical models a little later.
So yeah, this time we're going to sort of talk about ways of building more complex models and introduce this idea of a graphical model, which is a sort of visual language for describing those models. So we want to go away from these kind of simple models where we have to write everything down by hand and have simple formulas and kind of leverage the power of computation to deal with much more complex situations. So as motivation for that, let's recall our example from last time, the heights and gender example. So let me pull that up on a different screen. So remember, we had this example from last time where there was this data of different people's heights. We looked at the distribution, and it wasn't really Gaussian. It seemed kind of maybe multimodal, definitely kind of broader than a Gaussian. But then we saw once you kind of condition on gender, then you get this it's much more Gaussian distribution. And here, like, gender is observed, but maybe you wouldn't always have that observed, and you would just have a database of people's heights. So if we were trying to sort of model this well, how would we model it? So let's just think about that. Let's see. Can still see the screen? Yeah. So how can we model this? Well, we might say for each person I, they have some gender, which we'll label as sort of a binary variable, zi in 0 or 1, and then height xi, which is some positive real number. And of course, there's like already some problems with this where gender isn't quite binary and there's going to be edge cases, but we can sort of start with this as a simpler model. And then we might say, okay, well, how does the height vary conditional on the gender? Well, it's going to be normal distribution with some mean that depends on the gender. And so we'll call that, we'll say there's sort of two variables, right? So you're saying if we want to kind of model this two Gaussian distribution, we'd say, okay, there's this extra variable called gender, and then the height condition on gender is going to be a normal distribution, but the mean of that normal distribution is going to depend on the gender. So there's going to be like a mu0 and a mu1 for male and female heights. And for now, let's assume they have the same standard deviation, although in principle, they could have different standard deviations. So this is kind of a simple model we could write down. And just as a notational thing, this n I'm using means normal distribution. So if you see n of something and something else, that means a normal distribution with some mean and some variance, and meaning the probability distribution sort of follows the formula written to the right. And then we're not done yet, right? Because we need to also specify a probability over the gender. So we could say, okay, what's the probability that your female, say it's, let's say you're female with probability pi and male with probability 1 minus pi. And so this would be a full Bayesian model that kind of has everything specified. And I want to introduce just a little bit of terminology, which is the idea of a hyperparameter. So these are these kind of like unknown variables that are kind of like needed to specify the model, right? This like mu0, mu1, sigma squared, and pi. And we'll talk about how to get those later. Sometimes you just already know what they are. Sometimes you'll fit them to data. Sometimes you'll actually just specify a prior over them and then sample from that prior. But for now, just keep in mind there's kind of these hyperparameters we have to deal with. So this is a model we could use to sort of talk about this height and gender example. But the way I've written it down, it's maybe not that nice to deal with. I mean, there's kind of just a lot of symbols here, right? And like we can look at the symbols and kind of understand what's going on, but it's not immediately apparent how kind of all of the variables interact with each other. And so I want to present an alternative way of writing down a model like this that makes things a lot more transparent. So we have, again, these people, 1 through n. So I'm going to write down kind of a graph, like a graph in the sense of nodes and edges. So we'll say, okay, we have kind of first the gender, right? So there's these like Z1, Z2 through Zn. And then once we know the gender, we can sort of say what we believe about the height. Although I also need to know what these hyperparameters are. So those are also going to affect these. And then there's also pi, which is going to affect the probabilities of all these genders. And so this right here is what's called a graphical model. And I'll be a bit more precise later on at exactly like what a graphical model, like how a graphical model relates to the algebraic form of a probability distribution. But hopefully you can at least see intuitively how this is kind of capturing the dependencies and the structure of the model, right? Each arrow kind of tells you, like if I look at a node, the arrows coming into that node tell me what other variables in the model I need to know about in order to know the distribution of this variable. To know the height, the distribution of the height of person 2, I need to know their gender, and I need to know kind of these hyperparameters for the height distribution. So are there any questions about this so far? Okay, great. So the other thing is we'll often shade in variables that are observed. So let's imagine that I know everyone's height, but I don't necessarily know their gender. Then I would shade in these X variables so that I kind of know that these things are observed, the other things aren't observed. So I need to somehow make inferences about them. What does the pi represent? So the pi is the probability of being female. So it's going to be probably close to 50%, but it might be, actually in most populations, it's slightly off. I think it's like very slightly more than 50% of people are female, if I remember correctly. Yeah, and it's one of the hyperparameters in the model. Okay, so let's go back to the slides. Okay, so that was an example of a graphical model. It's a special case of a more general type of graphical model that we call a latent variable model. So a latent variable model is something that has, at a high level, this structure. It has some hyperparameters, and the hyperparameters can affect both the distribution of some latent structure and some observed output. And in this case, the hyperparameters, so you could think of this kind of general structure, think of each of these three nodes as potentially representing multiple nodes. So the hyperparameters in our previous case would have been this mu1, mu2, sigma, and pi. The latent structure would be the gender of each person. So there would be like Z1 through Zn, and then there's some observed output. So as written, this doesn't help us that much because it's kind of a bit too generic to really restrict the distribution much at all. But it's a kind of general type of pattern that shows up a lot where you have these hyperparameters latent and observed. And next we'll go through kind of several examples of how that might show up. So one special case of a latent variable model is something called a Bayesian hierarchical model, where there's a bunch of independent latent variables. And then there's a bunch of observed variables that are independent once I condition on the corresponding latent variable and the hyperparameters. So that was exactly the case in the gender and height example, where the height of one person is independent of the height of other people once I condition on gender and condition on the average height across genders. But there's other examples as well. So I want to give you actually an example from a recent paper that actually one of your GSIs helped write. Mihaela was one of the people who wrote this paper. It's a Bayesian hierarchical model for performing a meta-analysis of COVID transmission rates. So this is a very pertinent real-world example, but we actually already know enough to kind of talk about what's going on here. So I want to do that on the board, so I'm going to share from my iPad again. So let's talk about the setting here. So this is a meta-analysis of COVID household transmission. So the basic question is, if someone gets infected by COVID, how likely are they to transmit to a family member, or I guess in general, a household member? And this probably actually has a name. It's called the secondary attack rate, or SAR. So I mean, don't, that's not really necessary terminology to know, but just in case you're curious, that's what it's called. So this is a question that obviously is quite important to know the answer to. But unfortunately, in general, we mostly only have kind of small and in sometimes somewhat conflicting studies. So the way you might get information on this is there will be some study. It kind of tracks infected people plus household members. And there might be, you know, this is kind of some population of like some infectable population. And these studies are pretty small, so they might have anywhere, maybe like 10 on the upper end. Maybe they'll have, what was the biggest one, Mihaela? It was like a few hundred or something.
No, I actually had a few that were in the thousands.
Okay, so it could go up to like a few thousand or something at the highest end. But there's kind of, we want to somehow pool all of these studies together to get some general estimate. So the way we can think of this is for each study I, first of all, there's some value Ni, which is the total number of infectable people. And then Ti, which is the number of people who test positive. And then we might say there's some parameter pi 0, 1, which is the secondary attack rate. So then if we wanted to start drawing a graphical model for this, there's, well, let's just, yeah, okay. So there's pi, and then there's all the different studies, right? So there's like N1, N2, up through NK, if K is the total number of studies. And then there's T1, T2, through TK. And actually, I'm going to have you guys help me fill in the rest of this graphical model. So first of all, I want to color in the variables that are observed here. So which of these should be shaded in for being observed? So let's see some answers. Yeah, so T definitely, because those are the number of people who test positive. But also a few people said this too. N is also should be shaded in because we know the total number of people as well, because we can just like go to the houses and count the number of people. So we know both of those, and we don't know pi, so pi shouldn't be shaded. Okay, so next, where should I draw arrows? I guess maybe, yeah, okay, so pi to t, so that's one set of arrows. And then where else should I have arrows? Yeah, also from n to t. Okay. Okay, so then this would be a graphical model here. There's a few problems with this model. So, I mean, this is a valid graphical model, and it correctly captures kind of what I said above. but there's actually a few ways in which it doesn't match reality, or rather where it's kind of unlikely to fully match reality. So can anyone think of potential problems with this model as I wrote it down? So I'll give you a hint. So one of the problems has to do with stuff that Mike talked about. Okay. So someone, I guess Sana brought up one good point. I'll get to that one in a second. I'll finish my hint first. So Mike talked about sensitivity and specificity. And those are going to matter here. Oh, and I see actually, okay, Alexandra brought that up. So when we do these tests, the tests actually have some false positive rate and some false negative rate. And it turns out, so this is one issue, false positive rate and false negative rate of the tests. And so in particular, it turns out that for COVID tests, the false positive rate is very small, but the false negative rate is quite large. It's something like 15 to 30%. So there's actually going to be quite a few people who don't test positive, but actually are positive. And so we should actually have an additional variable. Let's call it the false negative rate. That's also going to affect all of these. So that's the first point. So Sana also brings up a good point, which is that these infections aren't really quite independent. So if one person, if there's multiple people in a household and one person, like say there's 4 people in a household and person 1 infects person 2, then if person 3 gets infected, it could be because person 1 infected them or because person 2 infected them. And that's another good point. I think we ended up ignoring that particular issue in this model, but if you were being really careful, you would want to account for that as well. And there's actually one last issue that you might want to account for here. Missing data. Okay, yeah, so it turns out also for some of these studies, they tested everyone. And for some of these studies, they only tested people who were symptomatic. And it depends on the study. So there's also, in addition to the false negative rate, there's an asymptomatic rate. And so that's also going to affect not all of the studies, but like some subset of the studies that only tested symptomatic people. And then the final thing, I guess, is that there's heterogeneity. So what I mean by this is that there's not actually a single SAR. There is a different secondary attack rate for each study. And that's going to depend on, things like people's behavior. So for instance, maybe in some place, people are kind of taking COVID much more seriously and practicing better hygiene, so it's lower. Maybe in another place, household sizes are bigger, so that could make things higher or lower. So we actually don't want to have this single pi. What we want is a different pi for every single study. Oops. But if we do that, then we've kind of completely defeated the purpose of doing a meta-analysis, because now we're just treating them all independently again. So we want some way of pooling these back together. So can anyone think of a way to kind of try to pool these pi, somehow combine these pies, but without forcing them to all be the same?
Can we pick the mean?
So yeah, we can basically form a distribution over the pies. So we can say all these pies, remember we had a beta distribution from before, and that's a good distribution over probabilities. So we can say that each pi is drawn from a beta distribution with some parameters alpha and beta. And have alpha and beta be hyperparameters in the model. And then we can fit these hyperparameters to data. And this is going to tell us something about the distribution of the pies, right? Given alpha and beta, we can figure out what the mean is, and we can figure out what the standard deviation is. So it both tells us what the sort of average value of the secondary attack rate should be, but also what the variability should be. And so this is actually the full, pretty much the full graphical model from this paper. And I can show you actually the results of this.
Jacob, I have a quick question.
Mm-hmm. Yes.
So like, why do we like use different pies, and like why do we use beta to kind of generate the pies?
Okay, right. So the reason we want the different pies is because for each study, there's probably a different secondary attack rate. For instance, some of these studies were done in China early on during the pandemic. Some of them were done in like the US or parts of Europe later on during the pandemic. And so people are probably behaving quite differently in those different cases. And so we don't want to assume that there's just a single secondary attack rate. We want to kind of model the variability of the secondary attack rate. And then the reason to have the beta distribution is we want some sort of common prior over the pies, so that we're kind of like pooling them toward, like, we kind of want to like use information about one to tell us about the other. Like if you tell me that like 5 of the pies are all between 0.2 and 0.25, then I'd probably believe that the 6th one is also between 0.2 and 0.25. But how do I sort of formalize that? I can formalize that by saying that they're all drawn from the same prior distribution. And then beta is just kind of, in some sense, a choice of convenience. I think you could have chosen other distributions as well. But you want some sort of distribution to do this kind of sharing of statistical strength across the different studies. Does that answer your question?
Yep, thank you.
Great. Okay, so any other questions? Okay, so let me just kind of show you the results just because they're kind of interesting. So I guess there's a bunch of studies, so the font's a little bit small, but we use this, so I haven't told you how to actually computationally actually compute the posterior here, right? That's actually quite challenging, and that's going to be the topic of the next several lectures. But there are ways to do it, and there's a nice software package called PyMC that you'll all get to play around with in one of the upcoming labs. And so you can kind of feed the data in there and get out posterior distributions. So the solid lines are kind of the posterior distribution over pi for each individual study. And then the orange thing is the posterior distribution over the average value of pi. So basically over the mean of the beta distribution. And so we kind of concluded that it was between 23% and 35% with pretty high probability. And actually several months later, there was a large scale study in the US that kind of got a pretty consistent value. So this was kind of a nice example of how a meta-analysis can get you something that's pretty close to the truth before you've done like a super large scale study. So the kind of key takeaway here is that Bayesian hierarchical models can help us model heterogeneity, right? It lets us model the fact that these different studies each have their own secondary attack rate, but while still pooling statistical strength to kind of get some aggregate estimate as well. So that's Bayesian hierarchical models. And that's one example of a graphical model. And we'll go over a few other examples next. So any questions about that?
All right, let's do an example of setting up a graphical model that'll kind of illustrate like how do we do it, what are the implications for a particular model that we draw, what are the limitations, what are the strengths, and so on. So we're going to try to model the Earth's temperature. So we're going to try to put ourselves in the shoes of like climate scientists who are trying to understand what is the Earth's temperature, many, many years ago. And what we want is we want to say, okay, I have for this year, here is the temperature. And I'm going to define the thing I want as H sub t. So the thing I want to know is H sub t, which is the temperature on the Earth's surface in year t. But I obviously can't observe that, right? I can't like go back in time. I haven't invented time travel. So I can't actually go back in time and figure out how hot the Earth was. But what I can do instead is I can go and excavate ice cores from the ice caps. And basically this is like looking at ice that's like that many years old. And I can go and measure concentrations of different elements in there. And specifically, I'm going to look at the concentration of heavy oxygen and deuterium. And these are just like variants on oxygen and deuterium that have like extra neutrons on the atoms. I'm not a climate scientist, so again, I don't know exactly the details. But if you're solving a problem like this, you're probably going to be working as a data scientist, like with a climate scientist. Or if you're a climate scientist, then you can use this knowledge that you have about climate science to do this. Okay, so I have H sub t, and I have these like quantities, the concentrations of deuterium and heavy oxygen. So I'm going to define big O sub t, which is the concentration of heavy oxygen at year t, and deuterium is the concentration of deuterium at year t. Right, so I have HT, OT, and D sub t, right? So these are all like three different quantities. H sub t is like the thing I actually want, and O sub t and D sub t are like the things that I don't want, or I don't know. Sorry, I know them, but they're not actually the thing I want, right? Like, but they're related. So in particular, they're related through the equation O sub t is roughly equal to some constant times h sub t plus some other constant. And it turns out that d sub t is also equal to some constant times this plus some constant. And these are sort of like parameters of the underlying physical processes, but I have some idea of what they are, right? And maybe they're not going to be exactly equal to what the physical process says because, the degradation, essentially like noise in the data, right? Like the data is not perfect. Maybe my readings aren't perfect, but roughly that's what I should expect. Okay, so now I have this setup. I have these things I observe, the oxygen and deuterium concentrations, and I want to understand what was the actual temperature. And I also have this setup where I have all this stuff at time t, right? So like I have the concentration like 1,000 years ago, and I have the concentration like 2,000 years ago. And presumably the temperatures should be linked, right? I don't want to set up a model where like they're all independent, because the temperature, like if we were in an ice age, like X number of years ago, then like X plus 1 years ago, we probably were also in an ice age, right? So there's some like relationship between the temperatures that are close to each other. So let's start by setting up a simple graphical model for this. We'll say h sub t is, we'll start with h sub 0, which is like the first year that I have data. And then from there, I can get O and D, right? And this is observed, so I shade it in. And now I have h sub 1, and I can get, or sorry, this should be zeros. So I get O sub 1 and D sub 1. And now I can do the same thing for H2 and O2, D2, and so on, right? And like I said, these aren't necessarily like independent, right? H1 is not independent of H2. So the way I'm going to set this up is I'm going to say, well, like H1 and H2 are related, but maybe if I know H0, maybe that's good enough to know H1. Maybe I, like the temperature in a particular year, maybe it just depends on the year before. This is a very, very oversimplifying assumption. We'll see, its limitations, but it helps keep the model pretty simple, right? Like you can imagine a super complicated model where I have like arrows going between like all the different H's, like every which way. That's pretty complicated. Generally, we want to incorporate complexity into our models when we need it. So let's start with a really simple model, and then we'll kind of build from there. So we have this model where, again, these are all observed, and these are set up. So each H0 only affects the one right after it and is only affected by the one right before it. That sounds kind of familiar, right? You've probably heard of this idea before in something called Markov chains, right? Remember, a Markov chain is just something where the state at time t only depends on the previous state, right? It doesn't depend on the state at times before. And so this is a really useful way of modeling things that change over time. It has its limitations, but it's also very useful. It's pretty well studied. We can really understand what's going on there. And so that's why this is called a hidden Markov model, because our hidden variables kind of form a Markov chain. The other thing is, notice that these observed variables only depend on the particular year, the temperature in that year, right? We're not drawing any arrows like this, right? Because if I know the temperature in a particular year, then that's all I should need to know to understand my readings, from my instruments on oxygen and deuterium. So this arrow, not including the red arrow shown in dotted red, seems like it makes sense, right? Like if I know the temperature, then that should be enough to tell me to reason about the readings I got, and vice versa. Now, maybe it turns out that, well, actually, those, what's in the ice cores is like from multiple years. And so maybe it does make sense to have those. Again, that kind of depends on the model. Again, another thing we could do to make the model more complex is to say, well, H2 doesn't just depend on H1, it depends on H1 and H0. I could even say that, well, it's like it goes forward even more, and so on, right? I can add all these arrows, I can make my model more complex. But the base version here, that without the red and green, this is called a hidden Markov model. It's pretty widely used. They're really like convenient, efficient algorithms for figuring out reasoning about the hidden variables given the observations. Okay, so I've drawn all these red and green arrows, but you might think, well, why would you need that? Like, shouldn't it be enough to have a Markov model? Well, not necessarily, right? So if we actually look at the data, this is actual data on temperature and concentrations of these different elements and so on. There's a lot going on here, but what I want you to notice is that there are these trends, right? There are these like repeating trends. The x-axis is time, and there are these repeating trends, right? There's like this peak, there's this peak, and so there's a sort of like cyclical nature of the data. That's something that a hidden Markov model can't capture, right? This cyclical pattern here depends on connections happening across, we're looking at what this is like 225,000 years ago. This is like 320. This is like 100,000 year cyclical pattern, right? So a Markov model is not going to capture that. So there's limitations. So these models are kind of useful for modeling simple cases of time series data, and they have their limitations. Okay, that's one example of a graphical model. Here's how you set it up. You draw your hidden variables, you draw your observations, and you think about what are the relations between them that you want to capture. So let's talk about how the probability distribution of the variables that we're interested in relate to the graphical model, right? Like, because we can like draw the graphical model and like it kind of makes intuitive sense, but what does it actually mean for the variables that we're talking about? Both, what does it mean about the probability distribution? Like, how do we write it out? And then B, what does it mean in terms of like which things are independent and which things are not? So let's go back to the hidden Markov model, right? Where we have a bunch of hidden variables, which I'm calling Z's, and a bunch of observed variables, which I'm calling X's. And remember, each Z only depends on the one before and after it, and each X only depends on the Z corresponding to the same time point. So the way we write out the probability distribution for this is we say, well, let's look at the graphical model and let's start at the root of the whole model, right? Like which little circle is like the parent of all the other circles. And in this case, that's simply Z1, right? It's sort of the first one. So now we can say, okay, this is probability of distribution of Z1 times, well, what's next? Let's look at all of its children. So we have its two children are X1 and Z2. So this is distribution for X1, which is conditioned on Z1. And then the distribution for Z2 given X2, right? And then next we go to X3 and Z3. So this is, I'm going to continue on the next line. Probability of X2 given Z2, because X2 only depends on Z2, and multiply that by the probability distribution for Z3 given Z2, and so on, all the way up to the very end, right? So the way that the distribution factors out is a direct consequence of the arrows in the graph. And so you can imagine if your graph has like, tons of arrows pointing everywhere, like lots of variables depend on lots of other variables, then these terms here are going to get a lot more complex, right? These terms are going to get a lot more complex. They're going to have a lot more terms in them. It's going to be a lot harder to work with it. And why is it nice for these terms to be simple? Well, let's suppose that you're trying to reason about, I don't know, let's say Z2, right? You want to understand like, what is Z2? Well, in this whole giant distribution, like let's say n is like 1,000, then there's a lot of these terms in this equation, right? But if we're looking at just Z2, it turns out that the only terms in this whole thing that depend on Z2 are these three, right? None of the ones in the future, because if you think about the ones in the future, we're kind of past Z2 and none of it matters, right? So in the whole thing, only these three terms depend on Z2. So maybe I can do some kind of clever algorithm where, I start at, 1, reason about it, and then I go on to 2, and then I go on to 3. And each time I only have to deal with a little bit at a time, instead of like having to try to like reason about 1,000 different variables all at the same time. So that's why simplicity in our graphical model makes our computation a lot easier. Okay, so this is what it means for the algebraic structure. The other implication it has is independence. So let's suppose that I have a random variable w, a random variable r, and a random variable u, right? So here, what this says is, there's some w, and that w is kind of related to r and related to u. So what happens if I know, suppose hypothetically that I knew what w was, right? Well, in that case, if I knew what w was, then this r and u seem kind of like, well, maybe they're not so related anymore, right? Because I know w. And we can see algebraically that this is the distribution for w, r, and u is equal to p of w, p using what we just learned, right? It's p of r given w, p of u given w, right? And again, you can see that if I know w, then the distribution for r and u are just the product of the individual ones, right? Like the conditional distributions are the products. So that means that r and u are conditionally independent given w. But notice that r and u aren't necessarily just independent, right? Like let's say I marginalize out w, so I integrated over all possible values of w, then these two terms are going to get linked together. So here, r is not necessarily independent of u, but r is independent of u conditioned on w, right? So graphical models tell us something about the conditional independent structure in our models. And if we go back to the hidden Markov model, you can see that like if we condition on Z2, then all of a sudden Z3 doesn't depend on Z1, right? Like let's say you didn't know Z2, you didn't know how hot it was, like in the temperature example, you didn't know how hot it was like 200 years ago, right? Then in that case, like the distribution for like 199 and 201, you kind of think they should be related, right? Like knowing something about 199 should tell you, well, maybe 201 was like relatively close. But now let's say that you were conditioning on Z2. I told you what Z2 was. I told you the temperature 200 years ago. Then, like the fluctuations from 199 to 201, knowing one doesn't necessarily tell you about the other because you've already established a baseline. And that's kind of the conditional independence structure that these graphical models capture. And we'll go into a little more detail on that later or in discussion.
So with that interlude and kind of complete, I want to go through our final example. It's going to be a somewhat more complicated graphical model, but it's going to teach us a pretty important lesson. I guess sort of the theme of today, and actually a theme of a lot of my lectures over the next few weeks, is going to be about the strengths and weaknesses of modeling assumptions. So what modeling assumptions can buy you, but also ways in which incorrect modeling assumptions can get you into a lot of trouble. And so we're going to in particular go over an example where incorrect modeling assumptions led to big problems for a lot of people in forecasting the 2016 election. So you might remember kind of famously at that point, many of the statistical models were saying that Clinton was almost surely going to get elected over Trump, but in fact Trump won. And so I'll try to explain from the perspective of graphical models why those models were getting things wrong. So that's the example we'll talk about, this sort of 2016 election forecasting. And so in some sense for election forecasting, what's our goal? Our goal is pretty much, we want to know the fraction of people who will vote for Clinton in each state. If we know the joint probability distribution over that, then we can sort of push that through the electoral college and then see the probability that Clinton wins the election. And okay, how do we actually kind of figure this out? Well, each of the 50 states has some number of polls. each poll, let's say it has like a pretty large sample size. So let's say it has a large enough sample size that we can treat the error as normally distributed, where the variance just depends on the total number of people in the poll. And so we kind of have some like these like independent Gaussian margins of error in each state in our observations. And then maybe we also have some prior over the fraction in each state. And then we can sample the true fraction of Clinton supporters for each state and look at how often Clinton wins the Electoral College. And so this is like simplifying things a bit, but basically something like this was what was behind the models that predicted 90% Clinton in 2016, even though Trump won. And so, I mean, of course, 10% probability events can happen, but I think 90% actually was kind of objectively too high of a probability to have for Clinton winning at that point. So there's a few things that are wrong with this analysis, at least two things. Can people think of sort of ways in which this model is too simplistic that in a way that would make it overconfident? So Daniel says these errors are probably dependent. So I agree with that. What would be like a mechanism for the errors being dependent?
There's another answer. It says polling may suffer may suffer bad cluster sampling. With cluster sampling, the data will be very dependent.
With cluster sampling, what do you mean by cluster sampling?
I don't know if Thomas wants to speak up. I guess if you like sample a whole family and you like count them all together, then
I see. Okay, sure. So like things aren't quite independent, so there's going to be some over dispersion because of that. So that's true. So if you actually just calculate the Gaussian standard deviation, assuming independence, that'll be too small. Okay, Daniel, I guess, also clarified what he meant. So you say the same trends in states with same political leanings. Yeah, so I think that's getting at it. So another way of putting this is that basically in different, so no poll is actually fully representative, right? So even if I call people up on the phone completely randomly, the probability that they answer is not one, right? Only some people answer. And different people will answer at different rates. And that rate is correlated with whether they're a Clinton or a Trump supporter. And in fact, some people also just don't have a home phone, or they might have multiple phone numbers. So basically, every poll has some inherent bias in it. And in fact, pollsters try to correct for this bias. So they actually, most polls are not based on just the raw sample. They actually kind of reweight the sample to try to account for these biases. But even after you do that reweighting, there's still going to be some bias left over. And this bias is going to be kind of, tend to be correlated across states for each pollster. So we should actually think of, instead of kind of thinking of you have all of these states that are independent, a better graphical model would be the following. So let's write this down. So a better graphical model would be kind of this grid graphical model where we have states on the one hand. So we have sort of states 1 through 50. And then we have pollsters. And so each pollster has, let's draw this. So each pollster has some bias. So let's say that there's biases B1 through BK for the different pollsters. And then each state has some proportion of supporters, which we can call P1 up through P50. And then if I have like some poll in some state and I observe some result, let's call this result like X1, 50 for the result of the first pollster in the 50th state. So this is a thing I actually see, at least if a poll was conducted. And that is going to be some, right, the mean is going to be more like B1 plus P50. Like it's going to depend on both the bias and the actual proportion of people. And there's also some additional dynamics, like the fact that things can sort of vary over time and stuff like that. But these pollster biases are kind of an important source of correlation, where if you don't model it, you're going to be way too overconfident because you think everything's independent, but there's actually these correlations. So yeah, so that's one important issue. It looks like people brought up some other issues. So polls could affect people's behavior. I think a kind of a generalized version of that is that there's actually time as an additional factor. So a poll from a month ago doesn't give you that much. It only gives you partial information about support today. Let's see, there's a question, what's pollster bias? Yeah, so the poll, like each poll is biased in the sense that like a given polling organization or a given polling company, their results might systematically lean conservative or sorry, lean left or lean right, in the sense that it might be over optimistic or under optimistic about the percentage of the Clinton vote, because of sort of the response bias of that particular poll. So that's what pollster bias is.
Wait, Jacob, why is the mean B1 plus P50 in this case?
So that's sort of how I'm defining the bias. I'm saying the bias of a poll is the difference between the true mean of the number of people who vote Clinton and the mean that the poll would observe on average. So I'm saying, like, if in state 50, the actual fraction of Clinton supporters is P50, but the poll would on average get something slightly different, let's say P50 plus some bias B1, then like I'm calling, basically B1 is sort of what I'm defining the bias to be.
I see, thank you.
Yeah. So I think another point, I think it might have been brought up in the chat, is that there's spatial correlation. So nearby states will probably have similar trends. And so this matters once we include the time varying nature, right? So once we sort of take into account that the vote share can change over time, and so past polls are kind of only partly indicative, if we treat that evolution as being kind of independent across each state, then again, we'll be kind of overconfident because we'll think that those kind of changes might on average cancel out to some extent across different states. But if we take into account sort of spatial correlations where like Wisconsin and Pennsylvania voting is highly correlated, then that introduces additional interdependence that should sort of further increase our uncertainty. So that would be like another major factor. And so I think like a kind of general takeaway here is that failing to model independence tends to cause you to be overconfident. So sort of modeling additional interdependencies will tend to increase your uncertainty because sort of you can have more correlated errors, which have a higher chance of changing the outcome. And this also is partly what underlied the financial crisis in, I think it was 2008, if I remember correctly, where people were sort of modeling the failure probabilities of different bonds, or sorry, not different bonds, different mortgages, I think, or something, as being independent, but they were actually dependent, and that kind of created this kind of catastrophic failure. So are there any questions about...
Yeah, sorry, can you repeat that? You said failure to model independence leads you to be overconfident. Is that correct?
Yeah, so failure to model independence generally leads you to be overconfident. Failure to model interdependence. So assuming that things are independent when they actually are not will lead you to be overconfident. Because if you treat things as independent, then you're kind of saying that the errors are going to tend to cancel out because they'll like kind of tend to not be all in the same direction. And so that's going to make you overconfident in what can happen.
Gotcha, thanks.
Any other questions on this example?
I think that was a good question where there's a lot of other sources of bias. Like, how do you know when you should stop modeling it?
Oh, how do we know when we should stop modeling it? That's a great question. So I think there's a couple answers. One is that in general, it helps to have a lot of domain knowledge. So I think just talking to lots of people who work on polling and on aggregating polls to understand what kind of effects might be present is probably one thing I would do. But the other thing you can do is something called predictive model checking. So basically what you can do is, this is something that's particularly easy to do in a Bayesian framework. You basically have all these variables that are in your model, and a bunch of them are observed. And one thing you could do is you can kind of like hold out some of those observed variables and fill them back in using by sampling from the posterior distribution. And so then you can sort of do a plot of like how those how your model predicts those variables will behave versus how they actually behave, and look to see if you can find kind of systematic discrepancies between what the model predicts and what the actual reality is. And so that's kind of another thing you can do, is you can kind of do these predictive model checks as ways of kind of like uncovering places where your assumptions might be wrong. What should we be asking to understand if variables are interdependent? So I guess I sort of answered that just now. Yeah, I think it can also just help to kind of like do thought experiments as well, like think about what kind of latent variables might be there. I think often the way you get independent or interdependence is because there's some hidden variable that affects multiple observed variables. So we're usually pretty good at immediately thinking of direct connections where two observed variables directly affect each other. But the more subtle ones that are like useful to explicitly try to think about is whether there's hidden variables that will affect multiple observed variables. And we'll actually talk about that more also during the causality unit as well. Any other questions? Great. So the final thing I want to do is just kind of set the stage for the next lecture. So far we've only talked about modeling, but writing down a model, we're not done. We still need to actually do inference, which means we need to compute the posterior. So far I haven't told you how to do that. And it's actually kind of not so easy. So, I mean, first of all, how might we do inference? So, like say in some general latent variable model, because ultimately, what do I care about? I care about theta and potentially also z, right? I care about the hyperparameters, what value I should actually choose for them, and I care about what the latent variable values are. So one thing I could do is I could place some prior on my hyperparameters and then just jointly sample everything. So basically ask for the joint probability distribution over theta and z conditional on x. What do I mean by sampling? Well, usually the most convenient way to get information about this posterior is to just be given a bunch of independent samples from the posterior. So basically see sort of a bunch of examples of what possible draws from the posterior would look like. So that's one thing you could do. Another thing you could do is, if I don't feel like placing a prior on theta, or maybe it just is sort of too much work, I could just try to do kind of maximum likelihood on theta. So I could maximize the log probability of x given theta, meaning I kind of marginalize out z, right? So this log probability is actually the log of some sum over all of the possible z's. And you might call this a sort of half Bayesian approach, where I'm being kind of Bayesian about z, I mean Bayesian about the latent variables, but I'm kind of doing maximum likelihood on the hyperparameters. So we won't really talk about that in this class, but that's another thing you can do. It leads to algorithms like the EM algorithm, which some of you might have heard of. But we'll focus more on this first method where we try to sample everything. But whichever of these methods we pick, we're going to run into a computational challenge. And one way to sort of see this is let's just think about how many possibilities are there for z. Right, so how many possible values are there for the latent variables? Well, let's go to the height and gender example, which is actually the simplest model we've worked with. In that model, let's say there's 100 people. Okay, so then there's 100 genders that I need to worry about. So I have these variables z1 through z100. And they're not independent, right? They're certainly not independent once I condition on x, because they're all kind of coupled by the hyperparameters. So I can't kind of just handle them independently. I actually have to kind of worry about their joint distribution. And so how many settings are there of these 100 genders? Well, there's 2 to the 100, and that's a lot, right? That's 10 to the 30. I don't even know what the prefix is for that. Let's see. So 10 to the 9th is billion. Trillion gets me 12, quadrillion gets me 15. I forget what comes after that, but I think you can sort of see, like, this is a lot of possibilities. This is with only 100 people, so you could have much more than 100 people. And so we at least can't do some algorithm that just exhaustively enumerates over all possibilities and kind of adds them up and normalizes. We need something more clever than that. And so we'll need a better strategy. And so there's this entire field of study on approximate sampling algorithms that can kind of do this efficiently. And we're going to start on that next time. And that'll be the topic of the next few lectures.